Hi everyone. So here you are going to learn on how to find the syndrome of cyclic codes. Okay, if you look in the previous videos, we already discussed about the syndrome, what is the meaning of syndrome, and how to find the syndrome of a NK linear block code. So now here what you're going to do is you're going to find the syndrome of the cyclic code, or you're going to learn how to implement the syndrome calculator circuit. That is the circuit that is used to calculate the syndrome. So we all know what is a syndrome, right? Syndrome is a to be saying it in very simple terms, syndrome is actually a set of code words which shows whether there is an error or not in your code word, to show that if there is any error or not. You see, because first you will be transmitting, what happens is that after when you encode U into V, and then you will transmit V, and after transmitting V, if the channel is noisy, sometimes there will be some error can occur, right? So if the error occurs, the receiver will receive another code word R. Instead of V, it will receive another code word called as R, and this R may contain some error pattern. And how do you find out if there is a mistake or not, or how do you find out if there is an error pattern or not, is by calculating the syndrome. If the syndrome is 0, that means no error has occurred. If the syndrome is non-zero, that means an error has occurred. Okay, and here you're going to learn one of the advantages of using the cyclic codes. Okay, so here also, as usual, the base of the story is exactly the same. Suppose the code vector V, just like how your NK linear block code. Okay, same thing. The assumption is all the same as your NK linear block code. Suppose the code vector V is transmitted. What is V? V is the n-bit code word. So it starts from V0 to Vn-1, is transmitted over a noisy channel. The received vector may be a corrupted version of the transmitted code word, or the transmitted code vector. Let the received code vector or received code word be R is equal to R0, R1, R2 up to Rn-1. So which means this is actually the corrupted version of this, which means here, if some of the mistakes takes place in any one of these bits, then that code word is represented by the R. So V, now in this explanation, V is the transmitted code word and R is the transmitted R is the received code word. The received code vector can be or not be any one of the 2 raised to k valid code vectors. We already know that the total number of messages for an NK linear block code, and hence for an NK cyclic code, there will be the number of the number of bits of the input message is k. So therefore there will be 2 raised to k messages. So which means for each of these messages there will be a separate code words. So which means there will be 2 raised to k code words, right? So if the received code word is any one of these 2 raised to k valid code words, then that no error has occurred. If the received code word is not one of these 2 raised to k valid code words, then it means that some error has occurred. So the function of the decoder is to determine the transmitted code vector based on the received code vector. So for that, the decoder first calculates the syndrome to check whether or not the received code vector is a valid code vector. If the syndrome is 0, then the polynomial of the received code vector is divisible by the generator polynomial. That is, we already know that V of x, right? V of x is equal to U of x into G of x, which then here you can see that here dividend is equal to divisor into quotient plus remainder, but there is no remainder over here. So which means that V of x is a factor of G of x. In the same way, I can also tell you that R of x is, so if R of x, if no error has occurred, then the received code polynomial is also a factor of G of x. Okay, so if the syndrome is 0, okay, if the syndrome is 0, it means that this is a factor of G of x. Now you can tell me yourself, if the syndrome is non-zero, it means that this received code word, or the polynomial of the received code word, contains transmission errors and it needs error correction. You see, so this is how we do it. That's what we do is we simply find the syndrome. And you know how to find the syndrome. We already know that how to finding the syndrome is actually very easy, because all you have to do is check whether this polynomial is a factor of g of x. G of x represents the generator polynomial. So all you have to do is simply check if this is a factor. So how to check? We all know for a simple arithmetic division, how to check whether a particular dividend is a factor of the divisor. All you have to do is check for the remainder. If the remainder is 0, then it means it's a factor of the divisor, or it's a factor of g of x, which means it is a valid code word. If the remainder is not 0, then that remainder is called as the syndrome, and that shows that error has occurred. So let the received code vector be represented by the polynomial r of x is equal to r0 plus r1x plus r2x square plus up to rn minus 1 x raised to n minus 1. Like we have discussed it, right? We all know what is r. R is the received code word or the received code vector. It's represented by r1, r2, r0, r1, r2 up to rn minus 1, right? So, yes, so this is an n bit. So an n bit code word has a degree of n minus 1. Okay, so and also we already know that r of x, right, is nothing. The received code word that we have discussed in NK linear block code also. But here I'm going to write it. I'm going to write the same thing in terms of its code word. So this is the code word. See, we already know that r, the received code word, is equal to the transmitted code word plus error pattern. If you want to write the same equation in terms of its polynomials, then it's r of x is equal to v of x plus e of x, where r of x is the polynomial of the received code word, capital letter V of x is the polynomial of this transmitted code word, e of x is the polynomial of the error pattern. E stands for the error pattern. We have studied this equation in the NK linear block code. So basically a cyclic code is also a NK linear block code. So which means the same equation can be applied for the cyclic code also. That's why that means this r of x is the corrupted version of the v of x. So the decoder of the cyclic code is supposed to define or supposed to find the value of v of x from r of x. That is what it needs to do. So for that, what it does is how to find whether this code word is a factor of g of x or not is the decoder will calculate the value of the syndrome. The decoder first calculates the syndrome to check whether or not the received code word. And how to check is it simply checks if the received code word is a divisible by g of x. It will check whether it is a divisible by g of x, or it will check if it's a factor of g of x or divisible by g of x. Because if it is divisible by g of x and if there is no remainder, then it means that this is a valid code word. Hence there is no error pattern. If it is a divisible by g of x, because we all know that we have already learned for the cyclic code, right? That is all the code word polynomial is divisible by, that's one of the properties of the transmitted code word. That is, the code word is a factor of the generator polynomial. All valid code words or all the valid polynomials of these code words are a factor of the generated polynomial. So if this is a factor, if r of x is a factor of the generated polynomial, then there is no error. Hence the syndrome will be 0. How to check it? Simply look at the remainder. To check if it is a divisible or not, simply look at the remainder. If the remainder is 0, hence no syndrome, hence it is a valid code word. If there is a syndrome, then we represent that using the equation q of x plus s of x by g of x. If you all remember, we already know that dividend, right? Dividend is equal to divisor into quotient plus remainder. Right? Dividend is equal to divisor to quotient plus remainder. So if I divide this entire equation with the divisor, I will get dividend by divisor is equal to quotient plus remainder by divisor. That is what I have written over here. Okay, you don't have to write this. This is just for your own understanding. So see, that's what it means. Dividend by divisor. Dividend by divisor is equal to quotient. So this q of x represents the quotient polynomial. Quotient plus remainder by divisor. You see, and this is what you call as the syndrome. This is how you represent the polynomial of the syndrome of the cyclic code, S of x and S of x. So how to find is simply by finding the remainder. That's all you need to do. Hence the circuit is very simple. You already know how to draw the circuit. You have already studied the circuit in the previous class. That circuit is called as the division circuit. The division circuit. The division circuit. How to use the division circuit is, the division circuit is a circuit in which you will be with the help of a particular divisor, you will be able to implement the circuit, and from the output first you will get the quotient, and that same quotient will be fed back into the input, and after when all the quotient is being given to the output, then the remaining values in the shift registers will be the remainder, and that remainder can also be taken from the output. So what you need is only the remainder. You don't need the quotient. Okay, so this is where the advantage of this cyclic code comes into picture. You see, because we already know, if I'm going to let me multiply this entire equation with g of x, then I will get r of x is equal to q of x into g of x plus s of x. Okay, and if I substitute this equation over here, I will get q of x, g of x plus s of x is equal to v of x plus e of x, right? And if I bring this over the side of the equation, this will become s of x is equal to, what is v of x? V of x is u of x into g of x. So u of x into g of x plus q of x into g of x plus e of x. Like I said, there is no negative over here because there are only two operations, XOR operation or the plus operation and the AND operation. That's all, right? So don't forget that. So this is equal to u of x plus q of x into g of x plus e of x. So what do you understand from this? From here you can understood that the syndrome of the cyclic code contains the error pattern polynomial also, which means that you can find the value of the error pattern from the syndrome. That is what this equation means. This equation means that the syndrome contains this information about the error pattern. That is the statement, that is the sentence. The syndrome contains the information about the error pattern. Alright, so what you need to do, all you need to do is find the syndrome and check if there is a syndrome or not. All you have to do is simply divide the circuit. Just divide r of x by g of x. That's all you need to do. Divide r of x by g of x. That's all. And after dividing it, if there is a remainder, then error has occurred. If there is no remainder, then that means the syndrome is 0, and that means it's a valid code word. Okay, so this is what. So all you need to do is, this is nothing. This is the same thing that you have studied before. The same division circuit. The circuit is exactly the same. So let me draw the general block diagram of the circuit. We all know how to draw, right? That is, first I will draw a XOR. Okay. At the input of every shift register, there will be an XOR function. So this is the first shift register, followed by an XOR, followed by another shift register, followed by an XOR, followed by another shift register, and it goes on and on up to the last will be a shift register XOR with another shift register. Oh my god, there's no space over here. What to do? I need some more space over here. Maybe I'll just redraw the circuit entirely and draw it small this time. Okay, I will draw it small, okay, because I need some space to draw the end. Okay. All right. Okay. And then, so this is your division circuit. I didn't draw completely. Just hold on. If I have to make a guess, I will draw. This is the feedback. This is the switch. This is the switch. And this is the switch. This is a switch. You don't need any switch over here, and you don't need any switch over here. This is a direct connection because there is always a connection. The switch means if it is open, no connection. If it is closed, there is connection. But at the first input, on the first operation, or how to say it, the first connection and the last connection, there is always a short connection. It will never be an open connection, because we have already learned that one of the properties of g of x is that the coefficient of the first term and the coefficient of the last term is always 1. That is why at the first connection and the last connection will always be a short connection. The rest of them depends on whether the coefficient is 1 or 0. So, okay, so this is basically G0. Okay, this is basically G0. If you want, I will name this connection, this line over here is called as G0. This switch is called as G1. This switch over here is called as G2. This switch over here is called as G0, G1, G2. This is switch over here is called as G3. Okay, and it goes on. This switch over here is called as G n minus k minus 1. This switch is called as G n minus k minus 1, and this switch, and all of them are all connected. Okay, and this connection over here is called as G of n minus k. Why? Because we have already learned that the degree of the generated polynomial is always 1. Always, right? The degree of the generated polynomial is always 1. So this is the circuit, and here you will have a gate. You will have a gate. Let me call this as gate 1, and here you will have another gate, and that is called as gate 2. This is called as gate 2. Okay, and then that will give you the, or it will feed back the values. This is the circuit. Okay, this is not over here, this is over here. We need to connect it over here. Okay, so this is the circuit. This is R of x. This is what you call as G0. Okay, the connection over here. So here, like I said, this connection, you don't need here, the XOR function is over here. Okay, I didn't see that, that's why. So this is the circuit. This is the circuit. This is basically your division circuit itself. All right, the division circuit itself. And by common sense, like I said, I have already told you that what you actually want is the remainder. This circuit over here, it will generate both the quotient as well as the remainder, right? It will generate both. It will generate the quotient as well as the remainder. But you don't want the you don't want the quotient. The quotient is totally useless to you. What you want is the remainder. And you see because the remainder represents the syndrome, right? So what you want is to find only the remainder of the division process. You don't want to find the quotient. So for that purposes only, we put gate 1 and gate 2 over here. Okay, so initially, if you all, so now if you know the working of the circuit, right? So what happens is that the division circuit working is that first the polynomial will be inserted in, or will be given as input into the division circuit, and as it goes into the circuit, as the sequence goes into the circuit, the division process will take place, and the quotient value will be found out. And after, when the quotient values all be found, these quotient values are now fed back into the input, because that is the process of the division process, right? When you divide the dividend with the divisor, you write the quotient, and after finding the quotient, you will multiply that quotient. you will multiply the quotient with the dividend to find the remaining values or to cancel out the divisor. That is what basically we are doing over here. That is, this process feedback means we are actually dividing it, right? We are dividing this. This is the r of x, and this is this is r of x, and this is g of x. Okay. So what we do is we find the code word polynomial, and then we multiply it and we write the value over here. That's what we are basically doing over here. We are multiplying, we are generating the quotient and we are feeding it back into the circuit. Okay, and then it's being shifted. Shifting operation takes place. So here first the quotient will be generated, but you don't want the quotient, right? So what you do is you will turn off gate 1. Okay, gate 1 initially. Gate 1, after when the sequence is entered in the circuit, gate 1 is off and gate 2 is on. So what happens is that the quotient will be generated, but that quotient will not go to the output because we don't want that output, and hence the quotient will be sent into the fed back into the division circuit, so that you can further division will takes place, right? And further division will takes place, and after when all the values of the input, okay, after when all the values of the input, that is r of x, after all the coefficients of r of x enters the circuit, then the quotient polynomial will be over. Okay, the quotient polynomial will be over, and then the remaining values, that is inside this shift registers, the remaining values, okay, that is inside this shift registers, the remaining values inside the shift registers are nothing but the remainders. They are nothing but the remainders. So what happens is that after when all the values of r of x enters the circuit, gate 1 turns on and gate 2 turns off, so that this will become, so because we need only the contents of the shift register, right? And we don't want any more division process to take place. The division process is complete, right? Finding the quotient and all is complete. It's all been fed back into the signal, and the division process is complete. Hence only the remainder will be left behind. So once when the remainder is already left behind, then this process will become nothing but a symbol shifting process. At that time, gate 1 will be turned on and gate 2 will be off. So all the values, the remaining values will be shifted into the output. That output is called as the syndrome, S of x. That is your remainder. So this is the working of the syndrome calculator circuit. Okay, so if I'm going to draw the same circuit using the 7/4 cyclic code, right? In your previous example, we used a 7/4 cyclic code, right? 7/4 cyclic code, in which the generator polynomial we have chosen is 1 plus x cube, right? So which means now I'm going to draw the syndrome calculator circuit of this cyclic code, so that I will get, this is nothing but, this is XOR function followed by your shift register. Okay, this is 1 plus x, 1 plus x, and there is no x square. That is why I'm not drawing any XOR function over here. That means the switch is open. If the switch is open, then the corresponding XOR function becomes useless, right? Because there is nothing to XOR. So if the switch is open, you don't have to draw the XOR function also. And this is your circuit. Here you have the gate 1. This is followed by gate 2. Okay, followed by gate 2, and this is your circuit. This is R of x. This is S0, S1, S2. Okay, this is your syndrome circuit. I forgot to put the arrow marks. Okay, there you go. G of x, this is what it means. G of x is equal to 1 plus x cube. g of x is equal to 1 plus x plus x cube. See, so here it is supposed to be 1 into x raised to 0 plus 1 into x plus 0 into x square plus 1 into x cube. That's what this means. So that's why this 0, it represents the open connection. That's why this connection is open. That's why there is no XOR function over here. So this is the syndrome. This is how you draw the syndrome calculator of a 7-fold cyclic code whose generated polynomial is 1 plus x cubed. Okay. And here you will get your syndrome S of x.